Hello students. Today in the unit 2.0, that is AC circuits, in the subject basic electrical and electronics engineering, we'll understand about purely resistive, inductive and capacitive circuits. Myself Chandrasekhar S. Patil, Sharad Institute of Technology, Polytechnic, Yatra. In the contents, we'll understand about purely resistive AC circuits, purely power in purely resistive circuits, purely inductive AC circuits, power in purely inductive circuits, purely capacitive AC circuits, and power in capacitive circuit. So, there any AC circuit consists of three components, that is resistive, inductive or capacitive circuit elements. It may consist of resistive, inductive or capacitive circuits. All practical electrical circuits consists of combination of three basic elements: resistance, inductance and capacitance. Any AC circuit you consider, there are three basic elements, that is resistance, inductance and capacitance. Now we will consider a purely resistive AC circuit, how it is represented mathematically and how the power in a resistive circuit is calculated. Consider a purely resistive circuit consisting of resistance R ohms. So here we have considered in the figure A AC supply and the purely resistance R of R ohms. Let an alternating voltage represented by the equation V equal to Vm sin omega t be applied across its terminals. As a result, an alternating current will be set up in the circuit. By Ohm's law, the value of the current at any instant will be given by I equal to V by R, that equal to Vm sin omega t by R. Okay. So any alternating, if you are applying an alternating voltage of V equal to Vm sin omega t across the resistance R, as a result of the alternating current, as a result an alternating current will be set up in the circuit because of the potential difference, because of the voltage applied across the resistance, and alternating current will be set up in the circuit by Ohm's law, that is given by I equal to V by R. By Ohm's law we know that I equal to V by R, that is equal to Vm sin omega t by R. The current I maximum will be Im, that will be maximum when sin omega t is unity. So when sin omega t is unity, at that time the current will be maximum flowing through the resistive element, that is the purely resistive element in an AC circuit. Hence, we can conclude that in a purely resistive AC circuit, the current set up by the sinusoidal applied voltage is also sinusoidal and both are in phase with each other. So, by we infer that by the current and the voltage are in phase, and the purely resistive AC circuit, the current set up by the sinusoidal applied voltage is also sinusoidal and both are in phase with each other. Even the current is also sinusoidal and the voltage is also sinusoidal and both are in phase with each other. So in a resistive circuit, there is no any phase lag or lead in this condition, and both the voltage and current are in phase with each other. The current I is given by Vm sin omega t by R, and Im maximum current is flowing through the resistive element when the current when the sin omega t is unity. That is, whenever the sin omega t is unity, at that point of time the current will be maximum. Power in purely resistive circuit. In the DC circuit, power in watts is given by the products of voltage and currents, that is voltage in volts and current in amperes. In AC circuit also, power at any instant is given by the product of instantaneous value of voltage and instantaneous value of current. Figure shows the power curve obtained by plotting the instantaneous values of power at number of points during the cycle. From the power curve, it will be observed that power curve, even though always positive, pulsates between 0 and a certain maximum value with time. Since the wattmeter indicates the average value of power over a period of cycle, it is of more practical importance. Note, in a purely resistive circuit, average power is given by the product of RMS values of the applied voltage and current. So, in a DC circuit, the power equation is given by the product of voltage into current. Okay. Similarly, in the AC circuit also, do we have instantaneous value of voltage and instantaneous value of current? The product of both of these gives the power in purely resistive circuit. So the power is obtained in the form of waveform. The power curve is obtained by the instantaneous values of power at the number of points during the cycle. So whatever the gray color is shown here, that indicates the power curve. From the power curve, it will be observed that the power curve will be always positive pulsates. It will be always positive between 0 and certain maximum value with time. So wattmeter reading, whatever the wattmeter reading we take for the power calculations, that is nothing but the average value of the power over a period of cycle. It is more of practical instruments. In a purely resistive circuit, average power is given by the product of RMS values of the applied voltage and current. If we want to find the average value of power, then we have to multiply the RMS values of the applied voltage and current. That is the wattmeter reading we are going to get in the practical experiments. Purely inductive circuits. Now we have understood what is a purely resistive circuit. Now we will understand purely inductive AC circuits. To summarize the important points in resistive circuit, we have that the always the current and voltage are in phase, or they are in line with each other. They are not out of phase. They are neither lagging nor leading. Voltage and current develop at a single instant of time. Even the power is given by the average RMS value of the applied voltage and current. So in the purely resistive circuit, the power is given by the product of RMS values of applied voltage and current. Both the voltage and current are in phase. The maximum value of current is given when sine omega t equal to unity, that is 1. Unity means 1. So whenever this I equal to I maximum current flows when I maximum current flows whenever the sine omega t Vm sine omega t by R is unity. Whenever sine omega t is in unity, at that time Vm by R is the reduced equation. Therefore, Im equal to Vm by R, which means that a maximum current equal to Vm by R, where sine omega t equal to unity in case of AC circuits. So now we will understand about purely inductive AC circuits. Consider a purely inductive coil with inductance L henries and almost negligible ohmic resistance connected across an AC supply as shown in figure 4.4a. So here we are considering an inductive coil with connected to an AC supply, as where AC supply is V equal to Vm sin omega t. Let an alternating voltage applied across the coil be V equal to Vm sin omega t. So whatever the voltage is applied across the inductance coil, that is V equal to Vm sin omega t. The resulting alternating current flowing through the coil will be set up an alternating field. The changing flux linking with the coil will induce an EMF of self-induction in it. So we have understood about self-induction and mutual induction. Similarly, in AC circuits, whenever an alternating voltage is applied across the circuit, inductive coil, the resulting alternating coil flowing through the coil set up an alternating field. So there is a changing field in the inductive coil. So always the field is changing with respect to applied voltage and current. So the changing flux linking with the coil will induce an EMF of self-induction in it. So it will induce an EMF of self-induction in it. We know that this EMF of self-induction will be always in opposition to the applied voltage and given by E equal to minus of L di by dt. So in an AC circuit, whenever an alternating voltage is applied across the inductance coil, we know that an alternating field is produced, and because of and an EMF of self induction is induced in it, and that EMF is given by E equal to minus of L into di by dt. Okay. Why minus sign? Because always the self induction EMF of self induction will be opposition to the applied voltage. So now, since the ohmic resistance of the coil is negligibly small, since the resistance is negligibly small, the applied voltage will have to overcome the EMF of self-induction only. So whatever the self-induction EMF in self-induction is induced, so the applied voltage has to overcome the EMF of self-induction only. Therefore, the applied voltage will be equal and opposite to the EMF of self-induction at every instant, that is V equal to minus of E, that is equal to L into di by dt. Okay, so the applied voltage has to overcome only the self-induced EMF because the ohmic resistance is negligible. Therefore, V equal to minus of E, that is equal to L into di by dt. Substituting V equal to Vm sin omega t in the above expression, we get Vm sin omega t equal to L into di by dt. So Vm sin omega t equal to L into di by dt. Di equal to Vm by L sin omega t into dt. Integrating both the sides, if you integrate both the sides, I equal to, instead of di means what? Small delta change in current. So if we integrate, then we get the current value, that is Vm by L sin omega t into dt equal to Vm by omega L minus of cos omega t equal to minus of Vm by omega L sin of pi by 2 minus omega t. Vm by omega L equal to sin of omega t minus pi by 2. So we get the current in the particular inductive coil flowing through the inductive AC circuit. So what is given? It is given by Vm by omega L sin omega t minus pi by t. So from the equation we have understood that whatever the voltage is applied across the coil, inductive coil, that is in opposition, it has to overcome only the self induction induced EMF due to the inductive coil. So that is always in the opposite direction. Therefore Vm sin omega t equal to L into di by dt. So di equal to Vm by L sin omega t into dt. Integrating now, because we are not finding the delta I change in current, but for the net change in current, if we want to find, then we have to integrate on both the sides. So integrating Vm by L sin omega t into dt equal to Vm by omega L minus of cos omega t, that equal to minus of Vm by omega L sin of pi by 2 minus omega t, that is equal to Vm by omega L sin omega t minus pi by 2. Okay, because we are taking the minus sign inside. So now we have understood how to find the current and voltage in a purely inductive AC circuit. Power in purely inductive circuit. How is the power calculated in the purely inductive circuit? Figure 4.6 shows the power curve obtained by plotting the instantaneous values of power at number of points during the cycle as before. Okay, so we have understood that the power is given by the instantaneous values of power at number of points during the cycle as before. V equal to Vm sin omega t, I equal to Im sin omega t minus pi by 2. Instantaneous power is given by P equal to V into I. Vm Im sin omega t into sin omega by t minus pi by 2. So now we can reduce it as minus of Vm Im sin omega t into cos omega t, that is equal to minus of Vm into Im by 2 sin 2 omega t. Okay. So in a purely inductive circuit, the power is given by the product of voltage into current. Now we have the instantaneous voltage as V equal to Vm sin omega t, and the instantaneous current as I equal to Im sin omega t minus pi by 2. So instantaneous power is given by P equal to V into I. So Vm into Im sin omega t into sin omega t minus pi by 2, that is equal to minus of Vm Im sin omega t cos omega t, that is equal to minus of Vm Im by 2 sin 2 omega t. Thus, the power curve is a sine curve of frequency double that of voltage and current waves. The mean value or taken over a cycle will be 0. So the mean value of the cycle will be 0. However, the power curve is a sine curve. Okay, always the power curve is always a sine curve in an inductive AC circuit, and the frequency is double that of the voltage and current waves. Okay. So average power equal to average of Vm minus of Vm Im by 2 sin 2 omega t equal to 0. This will also be clear that if the total energy supplied to the circuit during a cycle is considered, the shaded areas under the power curve of figure 4.6 represent energy. During the parts of the cycle when power is positive, the energy stored is in the magnetic field established due to the increasing current. This energy is represented by the area of positive loops. When power is negative, the same energy is returned back to the supply due to the collapse of the magnetic field as current decreases. The areas of the negative loops represent the energy returned back to the supply. The areas of the positive loops are exactly equal to the areas of the negative loops. Therefore, total energy supplied over a cycle is 0. Hence, average power P equal to energy supplied over a cycle divided by periodic time T, that is equal to 0. Thus, the average demand for power in a purely inductive circuit over the whole period is always 0. So here we can infer that average power equal to average of Vm minus Vm Im by 2 sin omega 2 omega t equal to 0. Means whenever in the positive half cycle, the total energy supplied to the circuit during a cycle is considered. The shaded area shows the power area. Okay, how much power is taken. So when the power is positive, at that point of time the energy is stored in the inductive coil. Okay, the energy is stored in the inductive coil. Whenever there is the power is positive, the energy is stored in the inductive coil, and whenever the power is negative, at that point of time the energy is given back to the supply. So because of that, the average power P over a period of time, over a period of cycle, is called as is always 0. Now we can infer that the average demand of power in a purely inductive circuit over the whole period is always 0. If you consider a whole period of cycle, single sinusoidal cycle, the average power demand of an inductive coil is always 0, because in the positive half cycle, the power taken is stored in the inductive coil, whereas in the negative half cycle, the energy stored is given back to the supply. Because of that, the average demand of power in a purely inductive circuit is always 0 over a whole period of cycle. So here we are clear that the voltage is V equal to Vm sin omega t, I equal to Im sin omega t minus pi by 2, and the instantaneous power is given the instantaneous power is given by minus of Vm Im by 2 sin 2 omega t. Similarly, average power is equal to minus of Vm Im by 2 sine 2 omega t equal to 0. So we have understood the significance of the average power P in an inductive coil. So whenever the inductance coil is in positive, the energy is stored in the inductive coil, whereas whenever the cycle is negative, the energy is supplied back to the given back to the supply. Thus, the average demand of power in an inductive coil circuit is always, for a whole period, is always 0. Now we will understand about purely capacitive AC circuits. So consider a capacitance C connected to the supply AC supply voltage. The AC supply voltage is given by V equal to Vm sin omega t. Now the current I flows to the through the circuit I, and that is going to the circuit capacitor C. AC circuit containing capacitance only. Instantaneous charge Q on the capacitor plate is given by Q equal to C into V equal to C into Vm sin omega t. The instantaneous charge. So as we all know that capacitance stores the energy in the form of charges, static charges. Okay, so energy is stored in the between in the plates on the plates. So that instantaneous charge on the capacitor plate is given by Q equal to C into V, capacitance into voltage. That is nothing but C into Vm sin omega t. If dq is the small change charge which accumulates on the capacitor plate in small interval dt, at that instant, when the current is I, then dq equal to I into dt. I equal to dq by dt equal to d by dt c into Vm sin omega t, or omega c into Vm cos omega t. I equal to omega into c into Vm sin omega t minus plus pi by 2. Okay. Current reaches its maximum value Im when sin omega t plus pi by 2 equal to 1. Substituting this in the expression 4.18, it can be written as I equal to Im sin omega t plus pi by 2. From the expression 4.20, we can find that the current varies sinusoidally and leads the applied voltage by 90 degrees. Thus, it should be remembered that when a sinusoidal alternating voltage is applied to a purely inductive, purely capacitive circuit, and the current that is set up varies sinusoidally with the same frequency as that of the applied voltage and leads it by 90 degrees. So, in the purely capacitive AC circuits, the maximum value of current at the expression for current is I equal to Im sin omega t plus pi by 2. So, I equal to dq by dt, change in charges, number of charges divided by the with respect to time. So, d equal to dt c omega Vm omega sin omega t, that is I equal to omega c into Vm sin omega t plus pi by 2. Always the current is maximum when sin omega t plus pi by 2 is equal to unity. From this we can infer that the power curve of a purely capacitive AC circuit is a sinusoidal waveform. Also, the maximum power is obtained whenever sin omega t plus pi by 2 equal to unity. Thus, it should be remembered that when a sinusoidal alternating voltage is applied to a purely capacitive circuit, the current that is set up varies sinusoidally with the same frequency as that of the applied voltage and leads it by 90 degrees. So, always the current leads the voltage by 90 degree in a purely capacitive circuit, whereas what it happens is the I equal to Im sin omega t plus pi by 2. The maximum current is a sinusoidal waveform. The purely AC in kind of capacitive circuit the current waveform is a purely sinusoidal waveform. Now we will understand about power in a purely capacitive circuit. So to find the power, we have the multiplication as V into I. V equal to Vm sin omega t and I equal to Im sin omega t plus pi by 2. Instantaneous power P equal to Vm Im sin omega t equal to into sin omega t plus pi by 2, Vm Im sin omega t into cos omega t. So that is equal to Vm Im by 2 into sin 2 omega t. Thus, similar to a purely inductive circuit, in this case also, the power curve is a sine wave of frequency double that of voltage and current waves. It means its mean value takes over a cycle is 0. Similar to an inductive coil, the power curve is also a sine wave. In the inductive coil also, the power curve is a sine wave, and in the capacitive circuit also, the power curve is a sine wave, and the frequency is double that of the voltage and current waves. Always the frequency is double that of the current and voltage waveforms. Its mean value takes over a cycle is 0. The mean value of the power in a cycle of sinusoidal waveform is always 0. Similar to that of an inductive coil, the power curve is a sine wave and the frequency is double that of the voltage and current waves, and the mean value is always a 0. Now we will summarize what we have discussed in a purely inductive, resistive and capacitive circuits. In a purely resistive circuit, the power curve is a positive half cycle, and it reaches from 0 to maximum value, and always the voltage and current are in phase with each other in a purely resistive circuit. Similarly, in a purely inductive circuit, whenever voltage V equal to Vm sin omega t is applied across the inductive coil, the power curve is a sinusoidal waveform, and the current lags behind the voltage by 90 degrees. Always the current lags behind the voltage by 90 degrees, and the sin omega maximum current is obtained when sin omega t minus pi by 2 is equal to unity. Thus the power curve is a sine wave of frequency double that of voltage and current waves. In an inductive, purely inductive circuit, the power curve, the frequency of the power sinusoidal waveform is always the double of the voltage and current waveform, and the current lags behind the voltage by an angle of 90 degree in the purely inductive circuit. Average power for power in a purely inductive circuit for a whole period of time is always 0. Means whenever the voltage is positive, sinusoidal waveform current voltage is positive, at that point of time the power is also is stored in the inductive AC circuit, and whenever the negative half cycle comes, the power stored in the inductive coil is supplied back to the supply, given back to the supply. Similarly, in capacitive AC circuits, whenever the voltage is applied, V sin omega t is applied across the capacitance, I equal to Im sin omega t plus pi by 2, and the sin omega t plus pi by 2 is unity. At that point of time, current is maximum, and always the current leads the voltage by an angle of 90 degrees. Always the current leads an angle. In a capacitive circuit, purely capacitive circuit, the current leads the voltage by an angle of 90 degrees. And also similar to a purely inductive circuit, in this case also the power curve is a sine wave. In this case also the power curve is a sine wave, frequency double that of the voltage and current waves. Frequency is always the double of current and voltage waves, and its mean value over a cycle is 0. Always the mean value of the purely inductive circuit or the purely capacitive circuit is always 0. So now we have understood what is the maximum current, what is the voltage, and what is the power representation in the, and we have also understood the conceptual wise the power in the inductive, resistive and capacitive circuits. So also we have understood that in a purely resistive circuit the power is positive and the frequency is same as that of the voltage and current. In the purely inductive circuit, the power is positive and our current lags behind the voltage by an angle of 90 degrees, and always the power is sinusoidal waveform in the inductive circuit, and also the average power is always zero. Also, in the capacitive circuit, it is similar to the inductive circuit, whereas wherein the power is average power is zero, the voltage leads the current by an angle of current leads the voltage by an angle of 90 degrees, and the total mean average power is always zero, and sine omega t plus pi by 2 equal to 1. At that point of time, maximum current flows through the capacitive circuit. So thank you so much.